Hi, my name is Bing Zhuo, a PhD candidate from the Technical University of Munich. Today, I'm going to use this video to introduce my research topic about how to sandbox AI-based unverified controllers via Safe-visor architecture in safety-critical cyber-physical system. First, I will provide you with some high-level idea about how this architecture works. Then, I will show you a demonstration for using this architecture on a physical testbed. In modern cyber-physical system, not of high performance but unverified controllers are expected to be used for complex tasks, such as artificial intelligence-based controllers, which are also known as AI-based controller. However, when we are trying to use this controller for controlling cyber-physical system, it is very challenging to ensure the overall safety of the system because we cannot verify the correctness of the controller at this moment. To cope with this issue, I explored the idea of sandbox from the community of computer security. Concretely, a sandbox would restrict the behavior of the untrusted component by isolating it from the critical part of the system. Then, the untrusted component can only access the critical part when it follows the rules given by the sandboxing mechanism. Here, I'm trying to sandbox unverified but potentially high-performance controller for functionality and safety by proposing a so-called Safe-visor architecture. Here's the overview of the Safe-visor architecture, which contains two main components. The first one is so-called safety advisor. The safety advisor only focuses on maximizing the probability of fulfilling the safety properties of interest. The second one is so-called supervisor. At runtime, the supervisor checks the input provided by the AI-based controller at each time step. Then, once the input from the AI-based controller is unsafe, the supervisor will feed the input provided by the safety advisor to ensure safety. Note that the supervisor will only adapt the input provided by the safety advisor whenever the input provided by the AI-based controller is unsafe. Therefore, we are able to exploit the functionality provided by the AI-based controller while providing formal safety guarantee. In our architecture, we consider off-the-shelf AI-based controllers, which mean that we do not have restriction regarding the type of the AI-based controller. And the main task for designing this architecture is to decide the safety advisor and supervisor regarding the safety properties of interest. Here is a demonstration of the Safe-visor architecture on a physical testbed in our lab. So we are considering the following scenario. A drone is tracking a virtual ground vehicle with the following safety specification. So the distance between the drone and the vehicle on both directions should be within minus 0.5 meters to 0.5 meters. Additionally, if the distance on this direction reach minus 0.3 meters to 0.3 meters at any time instant k, then this distance should be within minus 0.4 meters to 0.4 meter at the next time instant, and then it should be within minus 0.45 and 0.45 meters at the next time instant. So we have some temporal logic in the design safety specification. In the demonstration, we are using an unverified controller as on the left-hand side. So we are placing an unverified set point provider to provide set point to the position controller of the drone, which is an LQR controller along with input saturation. And the position controller will send the desired attitude according to the desired set points, and the desired attitude would be realized by the PID attitude controller. So in the unverified controller, the unverified part would be the unverified set points provider. In case 1, we are considering a running time horizon for 1 minute, and the virtual car is going to stay in the middle of the field. We are applying this unverified set points provider while we are replacing the set points provided by this provider with some faulty set points that will definitely cause violation between 40 seconds to 45 seconds. Here's the demonstration. In case 2, we deploy the same unverified controller, but in this case, the virtual vehicle is following an 8 dancing trajectory like this. Here is the demonstration. Thank you for listening. If you are interested in my research and have questions about them, please do not hesitate to contact me. Thank you.